In a typical data analytics system, there are a variety of technologies interacting. HDFS for storing files, Spark for distributed machine learning, pandas for data analysis in Python. Each of these different technologies has a different format for how data is represented, and there are plenty of other data formats represented in this ecosystem as well. Serialization and deserialization between these different formats causes significant latency across the overall system. Apache Arrow is a tool for improving performance of in-memory analytics systems, and today's guest, Uwe Korn, explains how Arrow enables these systems with interoperability that adds a lot of speed. This show goes into the weeds of serialization and deserialization in these types of systems and how data is represented. It's a very good show for somebody who wants to get an in-depth understanding of how this big data ecosystem represents data and how things can get sped up. If you're interested in subscribing to the Software Engineering Daily newsletter, you can go to softwareengineeringdaily.com. Also, if you're interested in collaborating, if you want to host a show, if you want to get involved in contributing to the outlines that I prepare for these shows, you can click on the link to collaborate on softwareengineeringdaily.com. On the website, you can also find links to the Slack channel, to my Twitter, and to my email address, softwareengineeringdaily@gmail.com. I would love to get your feedback. And with that, let's get to this episode about Apache Arrow and data representation in big data systems after a quick message from today's sponsor. If you want to learn about Kubernetes, go to apprenda.com/sedaily. Today, you can find a webinar about Kubernetes, covering microservices, persistence, and multiple clusters. You can also find links to a past webinar covering the history, the origins, and the technical architecture of Kubernetes. The webinars at apprenda.com/sedaily are hosted by Joseph Jacks, a member of the Cloud Native Computing Foundation, who was previously a guest on Software Engineering Daily. If you're looking to move to a cloud-native infrastructure platform that works with your existing apps, you should also check out apprenda.com/sedaily. Apprenda provides cloud platform software that works with your existing applications and infrastructure. So if you're looking to migrate to cloud native, but you want to maintain your existing applications, you might want to check out Kubernetes and Apprenda. Thanks to Apprenda for being a sponsor of Software Engineering Daily. And if you want to learn about Kubernetes while supporting Software Engineering Daily, go to apprenda.com/sedaily. That's apprenda.com/sedaily. Thanks again, Apprenda. Uwe Korn is a contributor to Apache Arrow, a tool for improving performance of in-memory analytics systems. Uwe, welcome to Software Engineering Daily.
Oh, welcome.
So I want to start by talking about two types of data processing, row processing and column processing. And we'll have an overview of just kind of the processing landscape, and eventually we'll get into discussing what Arrow does. But let's start by defining these two types of processing, row processing and column processing.
Row processing is the typical use case you see in a web blog or so, where you look at, like in both cases, you look at a table of information where you have columns which are all of the same type and rows which all belong together, have information to the same entity. And in a blog, for example, you're looking at a Rowwise database where you're also interested in the content of the blog, the title of the blog, how many comments it has. Whereas in Columnar, you're more interested in everything which is one column. Like you want to select all blog posts on the same date by a really large chunk of users.
Right. And so columnar processing has become more prominent in maybe the last 10 years as we've gotten more and more aggregations of giant amounts of data, whether we're talking about IoT or weather data or aggregations of social media data, just these high volumes of metrics where we want to do a big aggregation or the average or find the minimum of one specific column in a database. So like in your blog example, maybe we have an extremely popular blog and we want to do analysis on all of the comments, all of the text fields of all the comments. So we have to aggregate all the data from just that column. What are the challenges of that columnar processing? What are the canonical challenges of columnar processing that we've encountered over the last 10 or 15 years since Hadoop has kind of ignited this big data revolution?
So the main problem is which you always have, you don't want to have too many data. You just are interested in a subset of the data, like this one column. And this is really already a huge chunk of data. And the basic problem is if you want to do any processing on that data, you only want to get this necessary column and don't have to go through the other columns while you're processing it. And this is already implemented in a lot of programs that you only access a single column and ignore the other data and don't need to exit it, like with in your AO from your hard disk. But there is no standard way at the moment how application accesses this data and how it could pass it on to another application.
Okay. So when I load a data set into memory with a data analysis tool like Apache Spark, how is the data set typically arranged? If I want to do some columnar processing in Spark, for example, how is that data arranged and how might that differ from other systems that I might pull it into memory with?
Because you want to do operations on each of those columns are normally stored in memory as a chunk or bit chunked, but each column is stored on its own. And there's a central like hash map or dictionary where you have the name of the column and a pointer to the location in the memory where the column is stored.
Okay, and so what you're saying is the way that data is typically represented in memory is row-wise. So if you have like a bunch of rows where you have strings in memory interspersed with some integers, and you want to only process the integers, this is a problem. So explain why that's a problem and how the system might do columnar processing despite this row-wise representation.
If you do columnar processing on this data, you normally will load each row and only look at the value of that column you're interested in. And even though if you have code written that can access this column value in each row, your CPU normally fetches the whole row at once and then discards all values that don't belong to that column. Because typically a CPU will fetch not the actual memory content you specified, but also will do some prefetching so it can really get faster. And on each fetch, there is a latency, and this latency can really add up. So even though your written code that goes through row by row and only accesses this column value, in the background, your CPU already fetched a lot more memory, and you're just waiting for this memory to arrive. And for each next row, you have to wait again the latency to get a row again. In contrast to that, if you already had a column noise in memory, the CPU would fetch the value for the first row, but also would prefetch the values for the next row, which also will give you a significant speed up.
Okay, so just to recap, the data is represented in memory. It's typically represented in memory in a row-wise fashion. And if you have a bunch of strings interspersed with integers, the processing system is going to have to step over, if it wants to get all the integers in these collection of rows that you've loaded into memory, it has to step over the strings in order to analyze each of these integers. Could you talk in more detail about how does this slow down the CPU? What kind of penalties are we paying in order to do this columnar processing on row-wise representations?
It's already a huge number of CPU cycles, which normally if you do simple operation in a CPU, it takes 1 or 2 CPU cycles. But just waiting for a memory fetch can take you like hundreds of thousands of CPU cycles where you're waiting and just wasting CPU time. So it really sums up significantly to overhead you're having we're waiting on the next value.
Okay, and what's going on in let's talk a little bit more about the interaction between main memory and the CPU cache, because as we're getting into Arrow, the difference between main memory and the CPU cache is going to be important. How does information typically get from main memory and into the cache of the CPU?
Normally, everything, when you fetch something from memory, starts with an instruction in the CPU, which says, okay, I want this kind of integer from memory. And then your CPU sees, okay, the integer is located at that position. And it thinks probably you want to access the data that's the next kilobyte, which is also in that area, because your memory bus can fetch like a kilobyte or sometimes or many more kilobytes at once, but only at the cost of the latency of one memory request. And as this cannot fit into the registers of a CPU, your CPU will store this in the cache, so that if you have subsequent accesses to these memory locations or to its neighbors, it's already in the cache, and you don't have to go to memory again.
And how does the speed of main memory compare to the speed of the CPU cache?
I can't recount now exactly how much faster it is, but it's really significant. It's like 100 times faster.
So we really want our data in the CPU cache.
Yeah.
Okay. So with that said, what is Apache Arrow?
Apache Arrow, in its essence, is only a specification how you store columnar data in memory, giving it unified but also applicable to a lot of applications to store this columnar data in memory, so that you have kind of protocol how you can pass along this data. It's not only a specification. The Apache Arrow package already comes with kind of implementation for Java and for C++, how you can access this data, how you can generate those data structures, and there are also some additional libraries how you can persist this data on disk, so that you can actually already make use of it and have a simple way to integrate this into your application.
And just to recap, for people who still may be a little confused, what problem is Apache Arrow solving?
It's solving mainly the problem of integration of different columnar-based systems. Because at the moment, each of those systems has its own memory representation, which is normally really, really similar, but not exactly the same. And they have different APIs in each system, so you always need to write clue code if you want to pair two of those systems. Apache Arrow itself solves this problem by providing a bit of the clue, but also providing a common specification, so that these two programs can implement the specification and you can pass along the data without any overhead.
Could you give an example of a pair of systems that would want to be utilizing the same data, and contrast what they would have to do without Arrow versus what they can do with Arrow providing interoperability?
The typical example for this is if you're using Apache Spark and the Python library pandas. At the moment, Apache Spark has its native memory representation, which is different to that of pandas. And they two also have the separation that one is running in the JVM and the other one is running native code. So they're running at the moment in different processes and having different memory specifications. And to actually pass data from Spark to pandas, it has to convert the data several times, and this slows down the operation between those two, and the integration of algorithms you implement in Python, which are not, where there are normally already a lot of fast machine learning algorithms. It's kind of hard to integrate in Spark due to this kind of performance penalty you get through the existing clue code. With Apache Arrow, we would have a common standard how Spark would either store it internally in memory or translate its memory so that pandas could already use it. and didn't have to convert from Python objects to native objects to Java objects again.
So you're talking about the serialization and deserialization penalty that you have to pay in order to commonly share these objects.
Yeah, in the example of Spark and pandas, it's really a serialization that's happening there, which is very costly, but often it's just a bit simpler where you only copy data around and change the metadata for this. But as we're dealing with really, really large data sets, even a single copy of a data set could be too much. So we want to make sure that we only store the data once, even if we're using different applications.
What kind of implementations does pandas have to? Actually, I guess we should have a quick explanation. What is pandas and what is Spark, and why is this a canonical example? How do these two things fit together to be complementary?
Apache Spark is a distributed system for executing computations on large data sets, and you can do data analysis with it or machine learning. On the contrary, pandas is kind of doing the same, but it's not distributed. It's typically used in the Python world together with scikit-learn or so to do also machine learning in Python. It has a really fast native backend, and it's very popular because you can just easily start a prototype without having to start any servers or so. And you actually don't want to write algorithms for both. It's kind of nicer to write them in pandas and then just hopefully integrate that part into Spark or execute it directly, and don't have to have the overhead to re-implementing everything in Spark just to get an enormous performance boost.
How much work does a programmer have to do to integrate pandas and Spark today? Is there significant work, or is it more that the work is not that very hard, it's just the latency penalty you're paying?
At the moment, the work is not hard. There is already a toPandas function in Spark. The problem is just the implementation is very simple and not so fast as it could be. Just really, In this case, it's just a serialization penalty.
Okay, so when you're talking about getting a harmonious interoperability between pandas and Spark, for example, what kinds of implementation details do those involve in the respective systems?
In the respective systems, you would have to look at your data structure, at the data structure of Arrow, make maybe a comparison if your data structure is maybe already adhering to the spec. That's kind of what already was in mind with implementing or specifying Apache Arrow, that you make a spec that normally matches a lot of tools. Then you just need to gather the right metadata and then pass that along to the Arrow library so that another program can pick it up and use it. In the case where your data structures are not exactly the same, you sadly need to make some transformations, which have a bit of cost, but you only need to do the way from your application to Arrow. And if the other side already has implemented Arrow, there's no overhead for you to implement. You can just plug them together. And you only have to do this once and not for every other application you want to support.
Okay, so Arrow is this interoperability between a variety of different systems. Do each of these different? I mean, I guess give some more examples of different systems that things like pandas and Spark would want to integrate with.
There are a lot of those systems which store columnar data, like there's SQL and Hadoop engines like Impala, or databases like Kudu or so, which are becoming now popular. They have generic interfaces which you can use, but for each language they want to supply an API. They need to implement a new driver, take care of to get the glue code for those libraries to understand how the native format is represented in comparison to how they do it internally.
So you're now talking about data storage as well as data processing. How is data typically stored on disk in a big data processing system?
Typically, if you're just looking at flat files, there is the Parquet format, which is really, really similar to Arrow. It's a bit like Parquet was kind of the on-disk idea from which Arrow started. It's also really the default in now big data systems if you use files to load columnar data, and thus the design of Parquet and Arrow is quite similar. But also if you look at databases, they also store this data either in memory or on disk in columnar format, because they're also doing this columnar-based processing.
So data in the Hadoop ecosystem is often stored in HDFS, you're saying, in a binary format like Parquet or a text format like CSV. In any case, it's stored in a file. Or perhaps it could be stored in an online storage system like Apache Cassandra or HBase or Kudu, these online databases. If we're ignoring, let's ignore Arrow for a second, just to give people an idea of the status quo. When a computation engine like Spark or Impala requests data from one of these storage systems, what happens?
Typically what happens is the storage system in itself determines which data you need, loads this data into memory, it uses its internal data structures which were built with the software together, just with the use case of the software in mind, transfers this data to its API, and in the API or driver maybe, this data structure is transferred to the one which is retrieving the data, which in this case could be Apache Spark.
Okay, and when it's stored in a format like Parquet or a format like CSV, how does the loading into these in-memory systems, how does that go? Is it complicated to do a translation from the on-disk format of something like Parquet or something like CSV into the internal storage, into the internal in-memory representation in something like Spark?
If loading from like Parquet, it's not very hard to load because Parquet already has a notion of columnar data, and you already have some like metadata which specify how large it is. And even most cases in Parquet, the data on disk is stored similarly or equivalent like it is stored in memory for the solution you're using. In contrast, CSV is really more complicated because we have columnar data, but CSV is a Rowwise format. So we need to read this data Rowwise, determine its type or schema on the fly, and have to adjust our data structures in memory and their size continuously because we're only reading data row by row and we don't know beforehand how much data we actually read.
Why do we need Arrow when couldn't we just have the data in memory in the same format as Parquet?
Parquet has some optimization, so it's really good on disk. You can store it in plain format, which is similar to Arrow, but Parquet also has some optimizations to store it a bit efficiently. It encodes, for example, strings with a dictionary and then only stores the dictionary at the beginning of the file, and then specifies codes, integer codes, for each string, so we don't have to store any strings duplicated. This is really good if you're doing a scan over the data or restoring it from disk. But if you do random access on this file, you first have to jump to the dictionary or to the index, pick up the integer code, jump back to the dictionary, look what is this string for this integer, and you would have to jump from the beginning to the back and back again, which makes computations on this really inefficient. Whereas in Arrow, you already have columnar data which is stored in memory, so you can have fast scan access or fast random access to the data.
Okay, so with that said, what is being done to give these systems, these different systems like Spark or Pandas, what is being done to give them the ability to have data represented in the Arrow format rather than something else?
For the example of pandas, we already ship in the Python Arrow layer a conversion routine that converts the pandas data to Arrow data. In most cases, this is similar. So we just copy like the pointer to the data, but there's already some clue code which transforms on one or two pieces where data is not the same. Does a bit of conversion and serialization, but you actually normally just need to implement like the pointers to the data and then pass along the Arrow metadata.
How much does the programmer have to know about Apache Arrow?
So the programmer which develops Spark has to know how the Arrow format is specified and how it should pass along the data and how it can pass it maybe from JVM to native code. In contrast, the developer who's just using Spark and Pandas actually does not need to know about Arrow. It's just magically happening in the background. It takes care of passing the data from one system to another is fast, but it's really transparent to the user.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/sedaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/sedaily. It would support Software Engineering Daily and it would introduce you to the world of automated investing. Wealthfront.com/sedaily. Thanks to Wealthfront for being a continued sponsor of the show. Now let's get on with the show. As a data scientist, which you are, how does your workflow change? How does your workflow improve when you have these systems that are enabled by Apache Arrow?
The thing is, at the moment, without Apache Arrow, it's really hard to pass data from one system to another. The typical choice is you load data in one system, you work on it, and then you persist it on disk. And you use a common disk format to load it in the other system, which is really expensive because if you go from one application to another application, you need to store it to disk. Or if it's a bit better and you have an API between those two programs, you have one driver which passes it from one system to another, but you still need to have the separate code path each pair of the systems, which passes data from one system to another.
With Arrow, does that mean that on the same box, you're going to do some Spark processing, and then the data is going to be passed from the memory of Spark to something like Pandas? Or how exactly does that work?
As Pandas and Spark are both not, one of the systems is in the JVM, one is native. So they can't really run in one process. They could, but it's really not so easy. But there's already some implementation in the Arrow project which can pass data on the same machine from one process to the other without copying. And then the Spark process would write its data, the end result of a computation, to memory, specify this memory as shared memory, and then pass a pointer to the shared memory to the Python process, which then just can take on this memory and work on that. So that there's a common location in memory which both can access and read the data from, or write the end result to.
That seems pretty cool. Does that mean that you get to have, because my understanding is that in the past or in the present perhaps, you have to have different machines that are dedicated to running these different types of processing systems, or maybe you can tell me if that's wrong. Does Arrow end up cutting down on the number of machines you have running because you need fewer machines dedicated to specific systems?
Arrow is not cutting down on the number of machines you need. You actually can run them. You have to run them on the same system at the moment. Arrow is just cutting down on the overhead, which you have with working with two of different systems on one machine.
Okay. So in-memory data representation has been a desirable goal for a while, and each system has been handling it differently. Why has it taken a while to get something like Arrow going?
I think it's really out of the need to that you always have to write drivers or clue code to bundle two systems together. And we're getting more and more of those big data analytics systems. And the more systems you have, the more systems you need to support if you make a new system. And that's already amounts to a huge pile of work you have to do if you create a new one or want to have better integration with other systems. And Arrow itself solves this problem with having a specification you just implement once. And if there's other systems also implement that, you get integration with them for free, instead that you have to write your own driver again.
What I keep thinking about is the fact that each of these different systems, whether it's Spark or Pandas or Storm, has to implement the functionality to have the data represented in Apache Arrow. How laborious of a task is it to implement the specific formatting and representation for each of these different systems?
It really depends on the type of the system. Like for my example, in Pandas, it's really, really similar data structure. So there's not so much to do. There's some kinds of specialities, maybe like you have a different string representation, and then you need to change your strings. But typically, because you already have it column-wise in memory, and there are not so many representations how you could make it column-wise, you only really need just to have the right code to pass the data along.
So prior to Arrow, was the only way that data got moved between these different systems the process of you serialize it, you write it to disk, and then the other system that wants to consume it pulls it from disk, deserializes it, and converts it into its own format?
They were actually already doing it in memory, but how the conversion in memory was is not always fixed. Maybe there are already systems which have the same structure, then it's quite easy to pass along the data, but you never know if the system you're going to build now has the same memory representation as another system. Or maybe they're going to change later on, which is not directly visible to you. And then you don't have any guarantees that you can rely on that. So you have to write your clue code so that your data always matches the other data.
The Hadoop ecosystem is mostly Java-based, and you touched on this a little bit. Arrow improves interoperability with languages like R and Python. Explain how it improves that interoperability and why that's so important.
This is really important because R and Python are the typical systems which data scientists use if they're looking at small or medium large data sets, which can fit in your memory on one machine. There are a lot of, for most people, they're simpler to learn and to get started, but often they do not scale really good to really large data sets, and then you would need to re-implement that again in one of those JVM-based tools. But Arrow gives you kind of the freedom to still use those tools and just plug them into the JVM based tools without overhead. And therefore, we have to have a kind of code that supports memory management between JVM and native code, because at the moment they track the memory differently. And this is a bit a thing the Arrow library will handle in future, that you can have memory which can pass along between those two.
What are some of the other advantages of this interoperability? The overall interoperability of Arrow. Like, just, I understand at this point Arrow provides a vast number of interoperability features, but what are the other macro advantages of this interoperability?
It's already gives you the chance to have, if you're starting with a new software piece and you're not sure where you will execute it. That's kind of like, if you're starting an algorithm, implement it, and you're unsure if you're going to run it in Spark or if you're just using Python. If you implement it with Arrow, it just gives you in future the benefit of that you implement it once and then can just run it on one of those two systems, given that your algorithm works on a data which fits a memory.
Most of the data that we deal with today is not perfectly formatted SQL data. It's likely to be some denormalized JSON, and we might have JSON log data from one system that we're writing over here. Like, let's say we're writing weather data in one system, and in system A, and then we're writing weather data in system B in a slightly different JSON format. And then we might want to aggregate the data between these two JSON formats, despite the fact that they're not normalized. And so they might be on disk in a format that's not normalized. What are some challenges of dealing with, of building an in-memory columnar processing format for this type of data?
For this type of data, the basic thing you need to have is that your data structure supports big kind of nesting, because JSON data is not perfectly tabular, but it actually has kind of tree-like structure. But you also need to have kind of good conversion tools so that you can convert from one format to another. In the hopeful case, the data is in its binary form the same, but only has maybe other column names. Then you just can use the same data structures or the same pointer data location, memory locations, and just rename the column and give the pointer along. If it's in different memory representations between those two formats, then you actually have to write glue code.
Okay. So Arrow emerged out of the Apache drill project. Could you share some history behind that and how Arrow came out of that project?
I'm sadly not so involved in that, but all I could say is that the drill project is looking how they could integrate other languages into the system and how to support functions in those other languages. And they needed to look for a common format, how they could pass the data from one system to another.
Let's talk a little bit more about the lower level internals of this. We touched on this a little bit in the beginning. Explain, now that we've had more overview, how is, in the current systems that are not using Arrow, why is the CPU being underutilized?
If you're not using Arrow and you having not stored the data in columnar format, but in Rowwise format, the basic thing is like already told in the beginning, then you have to wait a lot longer time until your data gets from memory to your CPU, because you're reading a lot more data than you use, or you actually just have to wait more often for the main memory because you're just doing a lot more main memory accesses. And while you're accessing main memory, your CPU just does nothing.
Okay. And modern processors have an operation type called SIMD, which is single input, multiple data. Could you explain what SIMD is and how Arrow helps us take advantage of that?
If your processor has SIMD, it can do the same operation on like 4 or 8 values at the same time, and like nearly taking the same CPU time as it would just do on one value. The importance for this so that you can benefit of it is that you need to have the data stored like in a continuous fashion. There shouldn't be any gaps between the data. Then you just can load 4 values or 8 values at a time from main memory, which is hopefully already in your cache, do a computation on that, and start a restart of that again in the continuous memory region.
Okay. And what are the steps that you need to take in order to be able to take advantage of SIMD when you're writing Arrow?
The basic thing is just write the data in a continuous fashion, columnar fashion, and have each row value following another one.
Okay. And could you talk more about how Arrow improves the relationship between main memory and the CPU cache, and how Arrow encourages more, I don't know if cache affinity is the right word, more data in the CPU cache that you actually want to be accessing?
Arrow just defines the same way how you store columnar data. It takes a bit care of you that you have the right alignment in memory, so that it's starting at a 64-byte boundary, so that if you load data from memory, the data is loaded as a chunk, and that you can work like a SIMD instruction on that chunk, and only need one instruction to load it, and don't need 2 memory accesses to memory in one CPU cycle or one instruction of a CPU. And the basic thing really is only that, which Arrow does, is it defines the same way how you store the data. There's not so much magic happening, but that's also a bit of the essence. You have a simple memory access, and then the CPU can use all its internal powers just to compute things fast.
How are different companies contributing to this project and different organizations? What is the status of the Arrow open source community?
The open source community is still a bit small. It has quite some nameful contributors to it, but the thing is that Arrow is still in a pre-release state, and there's not really so much productive use of it already, because not everything is defined, and it's not at a release level where you could already use it in a stable software. So it's still a bit young, but it's already also the chance to get a bit involved, to have it formed like at the moment. But with those, with the small number involved at the moment, there are already a lot of names in there, which are part of really large companies and contributors to Spark or so on Impala, that should have an influence on its later future and its later usage.
What are the other types of real-world applications that Arrow will help speed up?
There's actually already one kind of real-world application where Arrow is used productively, which is a bit contrary that Arrow isn't a memory specification, but there is the file format Feather from Wes McKinney and Hadley Wickham, which is used to have a fast interchange for data between R and Python. This data format speeds up in a way persisting data for these data frames, as it uses the Arrow format to take the in-memory data, persist exactly this data to disk, and add a bit of metadata so you can load it in Python and R to support a really quick interchange between those two systems, so that if you're using Python and your coworker is using R, that you can work on the same data and have a really fast like loading and saving experience without having to wait on serialization overhead or being limited by the CPU time it takes to write to a format.
Okay. What are the further reaching implications of Apache Arrow? What are the future systems that it will enable?
The future systems it will enable is typically just the use of like different stack-based applications together. So you can easily integrate an application, two applications which use Columnar's data, but you don't have to think about so much about how you pass data from one application to another, but simply if one adheres to the spec and the other one just writes a wrapper to adhere to the spec, they can pass data along.
Okay. Well, what aspects of Arrow are you working on today?
I'm mainly working on the support of Python and the support of serialization of Arrow to Parquet. Because mainly from my point, I'm a Python developer at the moment, so I want to have data in Python, pass it along to other data systems like JVM, so I can integrate them in my workflow without having to code anything in the JVM. Even though I'm happily okay with coding in Java, it's always best to stick to one stack where you write your code. But with Arrow, you can use another stack to pass along the data and do work for you. For the Parquet part, it's just really interesting to have a good format where you can store large chunks of data, and you have a really fast way to get data from disk to memory and back again.
Okay. Can you talk more about what is involved in writing that?
The most things you need to care about here is check if the data structure in Python matches that in NumPy, in that special case, the library which we use for numerical computations in Python, matches the spec in Arrow. If it matches the Arrow spec, we can just pass along the data. If it does not match the spec, you have to spot differences and take care of that, like doing a conversion so that you can pass data from Python to like a native code or Arrow and back again. And the most important thing here is you have to look that you do with the least amount of data duplication in memory and do it efficiently so that your CPU can really pass it along and convert it really fast. Because this is a huge amount of data and this overhead is already very costly and you want to keep it to a minimum.
So we're talking here about the CPU bottleneck. That is the problem that Arrow is ultimately solving. What are the other bottlenecks that exist in the Hadoop ecosystem?
Also, the other main bottleneck, which kind of is also Arrow addressing, is the CPU to memory bottleneck, which can become quite significant if you have a lot of data in the memory and you pass along a lot to the CPU and back again. This is kind of the next important thing if you're having addressed the CPU bottleneck, but afterwards it's normally disk or network where you have to pass data around.
What is the finished product of Arrow going to look like? How far are we from having everything that needs to be implemented for this project to be a success implemented?
The finished product will be a specification, which we nearly have. We have to still do some refinement, and a bit of code, which is doing the data structures or the classes in code, so you can use from Java or C++ or Python, and a bit of conversion routines to the typical libraries you already have, like to NumPy or to native C++ vectors or so. And also the code that you can pass along memory stored in the JVM to native code, or memory stored in one process to another process, and pass along a bit of metadata so the receiving process knows where to exit the memory. And there's also a main important part that those round trips are tested, so you can be sure that when you pass memory from the JVM to native code, it will work.
So row-wise and columnar-wise representations, it might seem like these are the only types of representations that we're going to want to have for our big data workloads. But I can imagine something like TensorFlow, perhaps standardizing or changing how we look at our workloads, such that we would want an entirely new format of representation. Do you think that's plausible, and how would we adapt to? Well, I should just ask. Do you think that that's plausible?
There's a bit like having to define a bit what your requirements are. The basic requirements of Arrow is, for example, that you have data stored in memory, which is not in a compressed or encoded form, where you have fast random access. And for that, there are only really two plausible things how you can store it in memory. It's either row-wise or column-wise for fast random access. That's because we're dealing here with kind of like a 2D table, but our memory is linear, so we need to have some form of linear transformation. For contrast, other applications where you have large matrices which are sparse, it may be just a good implementation just to store data, only the data points were actually as a value in it, and not store a large chunk of nulls in it. But for the point of Arrow, we're mostly interested in data where we have fast random access and the whole data is stored without any compression.
Are there any types of workloads where Arrow is not a great fit?
So like the typical use case I had in the beginning, like with a weblog, where you look at a page, there's an article, and you're only looking at a row of your table. Then you have a database in the back end which should store the data row-wise, because otherwise you would have to fetch a lot of columns and a lot of data which you don't actually care about. And in this kind of use case, columnar data is not really fitting, and Arrow that does is not fitting.
Cool. Well, Uwe, thanks for coming on the show. I think this has been a great overview of the Apache Arrow project. Is there anything else you'd like to say about the project in conclusion?
In conclusion, we're at a good state where we're defining now an Arrow, or have final refinements how the data structure should look like. We're starting a good implementation going onward in Java and native code and in Python. But the thing is now we're still not there. We still have to implement a bit. And the thing is it's now really a good point to also have a look at it and see how it matches your workload, and maybe even a small contribution, whether like mistakes in the spec would really help us, because now it's the time where we just nearly to the finish line for specification. And now it's time where we can easily correct errors. So yeah, take a look.
Great. Well, Uwe, thanks for coming on the show. I appreciate it.
Thank you for hosting me.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.